So who am I? I'm Eloi Benoist-Vanderbeken. I'm French and a little bit sick, so excuse me for my bad English or if I cough too much in the microphone. So I'm working for Synactive, which is an offensive security company. We have 15 ninjas in our team, and we are divided in 3 different pools. So mainly pen test, reverse engineering, and development. And I'm the team coordinator for reverse engineering. We have 21 reversers in the team, and we focus mainly on low-level development, reverse, and vulnerability research and exploitation. If there is software in it, then we can own it. Basically, everything from bootloaders to web browser or everything. And we are hiring, so if you're interested, drop us a mail. So, quick introduction. So, I'm going to talk about CVE-2018-4193. So, this is a vulnerability in Windows Server, which is a user-learned daemon in macOS, which is used to display Windows on macOS. So, for compositing and routing different events, like when you click on a window or when you try to displace things. So it was a bug discovered by Red 2 Systems and at least 2 others, Pontoon 2018 teams. I heard that a lot of people had this bug. So Red 2 Systems used it in the Pontoon chain to spawn a root shell, but their exploits took something like 90 seconds to work, and their exploit didn't work the 3 first time, and only the 4th, and in Pontoon rules you only have 3 attempts, so it didn't even work the day. The full chain is described in a very excellent blog post series that I invite you to read. And in the last one, they offered a binary ninja license to the first person who would publish an exploit that works in less than 10 seconds without crashing Windows Server, obviously, and with more than 90% of reliability. So I decided to give it a try. So the bug is very, very simple. It was found via in-process dump fuzzing. So there is an attacker-controlled signed index, and it can be used without a lower bound. So basically, you can access the 3rd element of the array. You cannot access the 10th element of the array, but you can access the -10 element of the array. So really a simple bug. But there is some limitation. The elements in the array must have a D-word equal to 400 and must be followed by a null pointer. And if those preconditions are met, then you have one heap pointer, which is written in place of the null pointer. And there is a Mac port name that will overwrite the D-word next to it. So the heap pointer points, for the moment, on an unknown object that wasn't described by a Red 2 system. So a little digression, maybe not all of you know what's a Mac port name, even if Tyler Bohan talked a little bit about that yesterday. So basically, it's just an ID which is used to reference a port, and the port is like a general mechanism used to send message both inter-processes and to kernel objects. So a Mac port name is basically a handle to talk with the kernel object or with the server. So this index is basically incremented at each generation, and there is a gen count which is used to make sure that if you reuse the same index, you don't have the same Mac port name. This is to early detect the reuse of a Mac port name, which was unintentionally freed and then reused. So this used to be 100% deterministic, and it was used by the attackers to hardcode some values in their exploits, most notably Mac task self port, which is basically a handle on the process. If you have Mac task port on the process, then you can read, write its memory, you can manipulate its thread. So being able to hardcode this value was useful in exploits. You can also send Mac ports to another task. So you could spray a lot of Mac ports and hardcode a Mac port name in your exploit. So you don't have to make any logic. You can just make a big wrap chain which send a Mac message containing the Mac task self to your exploiting process. And that just works. So since iOS 11, Apple decided to fix this. And now the namespace is randomized, which means you cannot predict what will be the next Mac port names that will be used by the kernel. But the 8 first entries are not yet randomized, so because of compatibility reason. So you can still hardcode Mac task self in your exploit. They also try to randomize the generation counter, but it is still initialized with 3 and still incremented by 4. The only difference is now the Mac port name cycle after 16, 32, 60, or 48 or 64 generations instead of 64 before. So you don't know how many times you need to reallocate a port to use it in your so it can be used by your victim. It was just a little digression. We won't talk about Mac port anymore. Just a quick recap about the vulnerability. So we can overwrite a null pointer with a pointer in the heap, and we can overwrite a D word with a Mac port name. Because Windows Server has a lot of different clients, we don't know what will be the Mac port names that will be used to override the D word. And we don't know either what's the value of the heap pointer which is used to overwrite the null pointer. So the Red 2 system exploits used the Mac port name to overwrite heap pointer. And they used a lot of heap spray to make sure that the overwritten pointer points on valid memory. And well, they did a lot of complicated stuff. I invite you to read their blog post to understand it. What you need to remember is the problem with this approach is because you are using a Mac port name, you may have to heap spray 4 GB of memory, which is okay for a point-to-own exploit, but can be very slow. So now I'm going to describe the exploit strategies that I used. So the first thing that I thought when I read their exploit was why not using the pointer value instead of the Mac port name? So the idea was to basically just find a null optional pointer, replace it with our unknown heap pointer, manage to free the associated object, reuse the allocation with controlled data, and then triggers the use of the optional pointer to gain code execution and execute our payload. So easy. Basically, I thought that I was going to find a way to place this pattern in memory, replace the null pointer with an overwritten pointer, freeze the object, reuse the allocation with controlled data, use the overwritten pointer, gain execution, and that's it. So basically, everybody knows that when you control RIP, everything is over. So the first thing we need to do to exploit our vulnerability is to find a null optional pointer that we can later replace. So fortunately, Windows Server gives us a really powerful primitive because we can set properties on a connection. that can be used on any connection. No privilege is required. And we can set arbitrary properties, and the values of these properties are Objective-C values that are deserialized from the user input. So, and later we can read, delete, and modify those properties. So this is a very convenient way to message the heap, or to read back modified properties, to leak values, or to place arbitrary data in the memory. So from the doc, we know that we can allocate a lot of different objects, so mainly everything that can be serialized through the Objective-C API. So that includes CF data, strings, arrays, dictionary, dates, Boolean, and numbers. So let's see what we can do with those objects. Because remember, we need to have the following shape with 400 D word, followed by a null pointer, followed by a D word that we can safely overwritten. So, well, how can we have these patterns in memory? So of course, we can use data or strings. So we just put the patterns that we want in our strings. Because it's Objective-C, we can have null bytes in our strings. It's not a problem. Even if it was, we can just use CF data. That was used by Red2 to get the Mac port name and pointer values in their exploit. But of course, that won't give you any code execution, because you are just modifying data. So we are thinking about CF array. If there is array, maybe you can put a null object in it and get the null pointer replaced. But actually, null Objective-C pointers are not really null. This is a special singleton object which is used to signify that a value is null. So you cannot have any null pointers in your CF array. Of course, date, Boolean, and numbers are useless. They are basically just values. So even if you manage to overwrite their values, that won't give you any code exec. So the latest object that we have left is a CF dictionary. So they use a hash table. And hash tables contain null pointers, so that's a win. And during hash table destructions, the allocator will just go through the whole hash table, check if the pointer is null or not, and if it's null, then it will be released. So we think that's a win, but not really, because remember, we have a CF dictionary, donc we have to override two pointers, the value and the key. Because if we only overwrite the value, then when the key will be destroyed, you will have a null pointer dereference. And if you just overwrite the key without the values, then the pointer will just not be used. Moreover, we still have the problem of the 400 D word to be placed before our null pointer. And we don't know if it's really safe to overwrite the D word just after our pointer in the hash table. So we need to go deeper. Fortunately for us, Core Foundation is kind of open source. Kind of because there was no update for 4 years, so the code changed a little bit, but the source helps a lot. And when you read the source, you find out that actually a CF property list created with data accepts 3 different formats. It first tries to decode binary format. If it doesn't work, then it tries to parse it as XML. And if it doesn't work, then it tries to parse the old plist format. For those who knows it, it's a JSON-like format. So let's read all the source code. XML and the old format are not really interesting. They're just basically a deserializer. But binary format, however, is a little bit more interesting, because it supports more objects than the other and more objects than what's documented in Apple documentation. Most notably, it can unserialize CF null and CF set. Something very, very strange in the code is that it supports deserializing, but you cannot serialize those values. If you try to use the API to serialize CF set, it will just throw an error, and you won't be able to serialize those values. So you have to forge your own CF set serialized value. And what's great with CF set is that it uses the exact same hash tables in the dictionary, but obviously there is only values and no keys in a CF set, so you just have to overwrite one null pointer to get code execution. But we still need to put 400 before on null pointer. So, for the moment, our battle plan become a little bit more clearer, well, something like that. We are going to create a CF set, and we will overwrite the null pointer with our heap pointer. So the question is, how are we going to put this the 0x400 before a null pointer? So the answer is again in core foundation internals, because some tiny objects are stored directly in their reference. That means that instead of having a pointer on a heap allocation, you will have directly the value in the pointer, which is not a pointer anymore. Obviously, it only works for small values that can be put in just a pointer. And so that saves some memory and CPU cycles, because you don't have to keep references on those objects, and you don't have to allocate or free memories when you are manipulating them. To identify those objects that are directly stored in their reference, the lowest significant bit is set, because every allocation is a multiple of 16. So if the lowest bit is set, you know that this is not a pointer from the heap. The next three lowest significant bit encodes the type of the object. So you don't have all those 3 bits that are used today. There is only 1, 2, 3, 4, 5 different types that are supported right now. And what you need to be careful when you use those pointers, because the tag type, that's their name, are lazy initialized. That means that if you try to overwrite a pointer with a tagged pointer which use a type that wasn't already used by the program, then the core foundation runtime, the core foundation runtime won't know this type, and you will crash your program. So Windows Server only use CF strings, CF number, and NS atom in his day-to-day life. We can force it to use NSDate by forcing him to deserialize NSDate. But for example, we won't be able to use NS indexed path in our exploit. So to make things a little bit more visual, here is 2 different tag type. The first one is a number. So we see that the lowest bit is set in both different tagged pointers. The next 3 bits is here. It's 3. So this is a number. The 3C is to signify that the object is a keyword, and the rest of the tagged pointer is used to store the value of the CF number. And this is the exact same things for the next tagged pointer, which is here a string. So now we know how to put a 400 before on null pointer. All we have to do is to put in our CF set a number whose the highest value of the number is 400. This way we will have a D word equal to 400 just before a null pointer. I hope this is clear. The problem is how do we make sure that, because remember this is a hash table, how do we make sure that our values are correctly placed in memory? The good thing is that CF set is a generic construction, so you can pass different, you can use it with basically every types, but because we are working with Objective-C objects, the CF set use built-in callbacks, so we know what the hash functions that will be used, and it is deterministic, which means that we can choose by brute forcing the lowest bit of our CF number, we can control where it will be placed in our hash table. So we can, because of that, we can put almost arbitrary keyword in CF dictionary and CF set in their hash tables. Of course, we won't control the lowest significant bit that encodes the types of the object, but that's not a problem since we just need to control the 32 highest bits of the value in our attack. So here I made a little animation. So we see that if we try to put in our CF set a CF number equal to this value that I want to read, it will be placed here, but we don't want it to be placed here, we want it to be placed just above. So we change the lowest significant bits of the CF number, we rehash it, we see where it will be placed in our hash table, and we change the value of the CF number until it is placed where we want, just before our null pointer. So the next things that are blocking us is what can we do is the value after our null pointer, because it will be overwritten with an unknown value, the back port name. So is it safe to erase this value here with a MAC port name? So fortunately for us, the answer is yes. Why? Because MAC port names are always have their two least significant bits that are set, which means that a MAC port name can finish with a 3, a 7, a B, or a F. 3, B, and F are not valid tagged type. So as I just said to you, said to you that using invalid tag types might crash your program. Fortunately for us, when we will destroy CF set to trigger code execution, the function that will be called is CF release. And CF release considers that if you are trying to release a tagged pointer, there is nothing to do because there is no allocation associated with that with tagged pointer. So it will just do nothing if the pointer is tagged. It doesn't check. It doesn't even check the type of the tagged pointer. So it's always safe to overwrite the next slot with a MAC port name, even if here the type is invalid. So for the moment, what we are going to do is to create a CF set with CF numbers starting with 400, followed by a null pointer, and we repeat this pattern everywhere in our hash table. When we trigger the vulnerability, one of the null pointer will be overwritten by a heap pointer, and the values next to it will be erased with will be overwritten with the MAC port name, but that won't have any consequence during the destruction of the CF set. So maybe you are wondering, what if the lowest bit wasn't set? That wouldn't be a problem either, because allocation size in the heap, that as I said, are multiples of 16 bytes. And hash tables elements count are prime numbers. So that means that there is always at least 8 bytes at the end of the allocation, which is not used by the hash table, but that was allocated by the allocator. So it's always safe to write the word just after the end of of the hash table. So even if here we had other things than a MAC port name, we would just have to put our anchor at the end of the hash table, and the MAC port name that is overwritten there won't be part of the hash table, but it will be part of the allocated of the memory allocated. So it's totally safe to overwrite this pointer here. So the latest problem that we have to trigger our vulnerability is, as I said, we can only specify a negative index. The problem is that the array which is used is global and really early allocated. So there is no way to control where the array that will be used during vulnerability triggering. We have no way to control where it will be placed in memory. And as you know, the heap grows forward. Fortunately for us, the base of the heap is just before the stack. So the heap cannot grow forward indefinitely, because otherwise it would override the stack. So if you read the internals of libmalloc, you will see that the heap first grows forward during 256 megabytes, and then it will grow backward by with chunk of 256 megabytes. So if we allocate enough CF set, after a given time, they will be placed before our array. We just have to send a lot of CF set to a Windows server. Fortunately for us, we can do this in just one operation by assigning a very big CF array of CF set as the value of just one property. So there will be just one message sent to Windows server to create this big allocation. So to make things clear, here we have got our heap. Underneath, we've got the stack. Here there is 256 megabytes of heaps that are reserved. So if we send CF set, a large array of CF sets to Windows server, they will be first allocated after the array, so we cannot access them with a negative index. But afterward, we see that a new allocation is made before, so now we can hit them with a negative index and overwrite one of the pointer of our hash tables. So now we have a null pointer that we can reuse. Now what we want to do is to free the associated object to oh, there is no much time left. It will be okay. We need to free the associated object to replace it with controlled data. So there is nothing really interesting there. It's just reversing the Windows server to find out what the allocated object is. It's actually an application, and you can create as many applications as you want from any client. The object can be freed without closing the connection. It's not that easy, but you can do it. So the idea is just after we trigger the vulnerability is to free the associated application, and now we just have to reuse the allocation to replace the object with control data. So as I said, we replaced a null pointer with an heap pointer. During CF set destruction, this pointer will be considered as a pointer on an Objective-C object. So I invite you to read the Nemo Frac article to understand how to exploit this kind of things. The main thing that you need to know is you have to overwrite the very first pointer of the allocation to control the ISA pointer. And obviously, you cannot do that by allocating Objective-C object, because Objective-C object already has this pointer set to specify their types. So you need to find a way to allocate control data where you control the very first D word of the allocation. So the first things you think about is just to use array. The problem with array is that they are immutable when you are using them to when you are deserializing them. So if they are immutable, their containers are inline allocated. This means that you never control the beginning of the allocation when you are allocating a CF array. Lucky us, CF set hash tables are not inline allocated. So we can again use CF set and forge a hash table where we will control the first D word, the first pointer, well, the first value of the allocation. So we just create a new CF set, and we will place CF integers at the beginning of it to control the first pointer of the allocation. Sorry, I made another drawing so you can understand. Here we'll build a CF set, and the first value of our hash table will be a CF number and will be considered as an ISA pointer when our overwritten pointer will be used. So now all we have to do is to message the heap to create holes for the application object, create a little bit tinier holes for all the other objects, so they don't use our holes reserved for application. We create our application. With some luck, it will be locating in one of our holes, which triggers a vulnerability. We freeze the application object, and then we reuse the allocation with our forged CF set hash tables. The problem is Core Foundation use the default heap as all C and C++ allocation made with malloc and U. And the default heap use separate magazine per core. This is to optimize the processor cache access and to reduce the risk of concurrent access to global heap structures. So this is problematic because if our application was allocated by a core, we need to use the same core to allocate our CF set. Otherwise, it will be locating in a completely different region. So you can find more information about the heap in the presentation I did in 2018 at Stack. I won't go into a lot of details in this talk because I don't have much time left. Just remember that we need to message all the magazine to make sure that we can reuse our freed application. So my first idea to message the heap was to use CF set. I mean, they already saved the day twice. Maybe they can save the day a third. Maybe they can save a third day. So let's just forge serialized CF set with duplicated keys. If we do that, the deserialization process should free a duplicated object when creating the CF set. The problem is that there is a bug in the deserialization process, and they never free a duplicated object because they consider that a CF set must be correctly serialized, so there is no duplicated keys. So they don't keep reference of they disable the reference counting when creating the CF set. So you cannot use CF set to message memory, but I drop a fantastic 0 day. You can crash Windows Server by making him creating a lot of CF sets with duplicated keys, and it will never free the allocation. So my second idea was just to use properties. You create a lot of properties. You delete some properties that will make holes. This is not very smart, but that works quite well. So in the process, I also create some applications because it seems to help Windows Server to switch from a core to another one. Maybe because there is some asynchronous operations used during application creation. I don't really know why it works, but actually it works. Maybe just a sleep would be enough. My exploit worked, so I didn't touch anything. And to debug everything, I just use my Heap viewer. So maybe I can show you how it works. So basically, it's just some PNG generated from a snapshot of the heap that I display in with HTML and JavaScript. And here you can see that there is a lot of well, maybe you can't see because it's too small. If I click on the picture, we see that there is a thread block of 0x 70 bytes and others that are 0x 60 bytes. So this is really useful when you are trying to message the heap to have a tool to visualize things. Yep. So, with some luck, we reused our thread object. So the next things to do is to trigger the use of the overwritten pointer to gain arbitrary code execution. So getting code exec is quite easy. You just have to trigger the use of our overwritten pointer. All we have to do is to delete the property associated with the huge CF array of CF set. So every CF set will be freed, and when our overwritten CF set will be released, our overwritten pointer will be used with a call to CF release. But the question is, how do we get arbitrary code exec? The answer is by forging a fake Objective-C object and a fake Objective-C class. The problem is that there is a lot of dereferences that are involved before getting RIP. Because you have your object that you dereference to get the ISA pointer, that you dereference to get the Objective-C class object. Then you've got a cache pointer that you dereference to get the function pointer. So there is a lot of different dereferences involved. So you need to bypass the ASLR to forge your fake object. For code, it's really easy because the system libs are loaded at the same address for all the processes, thanks to the shared cache. Well, even if that's not really true anymore on iOS 12, but that's another story. The problem is for data ASLR, sorry. Maybe we could try to leak the reused object address, like Red2 Systems did. The problem is that the allocation is really small. It's only 70 bytes, so it's hard to fit everything in it. I mean, the fake object, the fake class, and the payload. So what I thought was, well, macOS and iOS ASLR is known to be weak. I mean, there was several exploits that just hard-code addresses. The main recent one being the sorry my bad exploit for kernel vulnerability, where it just hard-code kernel heap addresses in exploit. So I thought it's not that uncommon to hard-code addresses in those systems, it seems. So I tried to study how the ASLR works in macOS. So the first thing that I studied was the heap allocation, because I can already message and allocate a lot of stuff in the heap. The problem is that the heap under macOS and on a 64-bit platform is really heavily randomized. I mean, you would have to spray 512 gigabytes of memory before being able to hard-code an address. So obviously, this is undoable. You could do it on 32-bit platforms, but that's not the point. So I looked at other means to allocate memory under XNU. And I looked at other ASLR mechanism. So the main executable is randomized with a random slide. But the random slide is quite small. It's actually only 256 megabytes, at least on a 64-bit platform. And the same slide is actually used for the stacks. That means that on macOS and iOS, if you have a stack leak, then you get a main executable leak directly for free. And the inverse is, of course, true. So I invite you to read the code of XNU to see that. And the dynamic loader is loaded just after the main executable, if it doesn't have a base address, which is the case on macOS and iOS. And again, 256 megabyte slide is used. So basically, when you create a process, you will have this layout. So the original base address is at the top of the thing. Then you've got a random slide of less than 256 megabyte. Your executable is loaded, and then another slide is added to the end of the executable. Again, less than 256 megabyte. The dynamic linker is loaded, and why am I telling you that? This is because when you allocate pages without specifying a base address, they will be allocated just after the main executable, unless a specific undocumented flag is used during process creation. But this flag is only used by Apple for WebKit. So that means that if we manage to force the process to allocate more than 512 megabytes of memory via MacVM APIs, then we can outcode the address of the pages. So imagine that this is the state of a Windows server when we exploit it. So we have some pages allocated just after a Windows server. And if we make enough allocations, we see that at a given point, we are 100% sure that we have our 50 or 41 values that will be at a given address. The question is now, how can I force a Windows server to allocate pages? The answer is actually quite simple. Windows Server is an old service, so it is not using XPC or NSXPC mechanism like the service Tyler talked about yesterday. So it is using an older mechanism, which is MIG. And for MIG function, that takes unbounded arrays as arguments to pass those values to the distant MIG functions. We send out-of-line descriptors. And all those out-of-line descriptors are sent. They are just copied by the kernel into the distant process. So because there is no limit of the size of the arguments that the MIG function can take, you can just ask XNU to copy 4 gigabytes of memory in the distant process. And that does work even if the undocumented flag is used, because the allocation mechanism is different, a little bit different from the VMMap API. This is also very fast because the memory is actually not really copied. It's only copy and write. So this is immediate. You don't have to wait for the copy to occur to send your message. So the strategy is just to reserve 4 gigabytes of virtual memory to allocate a page. We put our fake objective C class and with our payload in the page, and we duplicate the page. We remap it n times to create a big 4 gigabyte contiguous buffer, but which is only using one physical pages, so we don't have any problem of using too much memory. Then we call the set connection property to replace the big array of CF set with our 4 GB buffer. The buffer will be copied in Windows Server, and because we are allocating 4 GB in Windows Server, we can hard code the address of our fake Objective-C class in our exploit. Then our fake class will be used when the CF set will be destroyed, and MIG will automatically free our big 4 GB allocation. So, again, I made some schema. I don't know how you say schema. So it's a little bit more clear. So we've got our exploit. We reserve 4 GB of memory. We create our fake class and we put our payload in a page. We duplicate the page. We send the message to Windows Server. Then we can hardcode the address of our fake class here. And we will be able to use this address in our overwritten in our reused object. So now all we have to do is to ensure continuation of execution. So this is not really hard, because when our Objective-C, when our fake Objective-C object will be released, RDI will point on our Objective-C object, and we control our IP. So we could try to stack pivot and make some rope. That's what Red 2 systems did. But it's quite complicated to ensure a continuation of execution after that. For example, Red 2 systems, what they did is to allocate a fake stack and jump at the beginning of the window of messaging handling process. I found that it wasn't the most beautiful thing to do. So I decided to just use a pure jump payload. So I just jump, control the first value, control the value of RDI, and jump on a system to execute arbitrary shell commands. And after that, everything will continue like nothing happened. So, I will now show you how the exploitation works. So, this is the initial state of Windows Server. We first allocate our big array of CF set. Then we message the heap by creating a lot of properties in Windows Server. Then we delete some properties to make some holes in the heap. Then we create our application. With some chance it will be located in one of our holes. Then we trigger the vulnerability. This will replace one of our null pointer in our CF set with a pointer on our application. We delete the application. Then we try to reuse the memory by allocating a lot of, by creating a lot of CF set again. So you see that the pink rectangles don't use the biggest holes. This is because of how the memory allocator works. It will to make sure that the heap is not too fragmented. It will first use the 60-byte holes before the 70-byte holes. That ensures that our memory allocation will not be reused with CF set headers, but with hash tables, as we want it to be. Then we send, we call the set connection property again with our 4 GB buffer that will put one of our page at the hard-coded address. In the fake class, we can use pointers that are in the shared cache. because they are the same in both the victim address space and the attacker address space. Then all the CF sets will be released because we are redefining the property, so the old property is freed. This will trigger the use of our overwritten pointer that will execute our arbitrary command, and at the end of the property redefinition, the big 4 GB array will be freed. All we have to do next is to clean a little bit the heap by freeing the rest of the properties, and we are back to the initial state of the process. So I said that the exploit is stable. It is, but you know what it is. Yeah. So let's pray with the raccoons. Hop. And here we go. And here it is. So as we can see, the exploit takes 9 seconds to spawn to execute arbitrary commands. We could gain some seconds by hard coding the serialized CF set, which takes a lot of time to serialize. But because everything is hard coded, we could just put it in a hard coded buffer that we decompress. But that would make the code a little less readable. So because I'm still under 10 seconds, I decided to keep it like that. So what's great with this exploit is normally you can use it twice without crashing. So let's see if it works. It will take even less time because it works. It takes less time because the heap don't have to regrow. So here we have we trigger in 8 seconds only. So it worked. Great. So the challenge is complete. The exploit is really stable, like for real. Only the CVE, only one CVE was used. But it took quite a long time to get this exploit code working because I had to reverse quite a lot of different things. So it took 18 days to code just like 900 lines of code. But it was a lot of fun. The exploit source code is available. We tweeted it like 2 or 3 days ago. So you're welcome to just read it and reuse it and do whatever you want with it. So I would like to thank Red2 Systems for the challenge because, and the Binary Ninja commercial license that I won. I don't know if I will do a lot of things with it, but that's always great to have it. Thanks to Synactive for the times and the review and the awesome team. Thanks to OffensiveCon for the amazing event. And I don't know if I will survive to night party, but and thanks to my wife for letting me go to Berlin on Valentine's Day. And thank you for your attention. Do you have any question? I'm sorry, you're going to eat a little bit late because of me.
Not really a serious question, but what is the YouTube video in the comment?
Oh,
Can you play it?
This is a French song. Le Poinçonneur des Lilas. It's a song about a man punching holes in metro tickets. No other questions? Well, thank you. Bon appétit.